안녕하세요. 오늘 하게 될 것은 지난 시간에 하던 거 계속 하겠습니다. 하스킬로 리스프 짜는 거였는데 제 생각에는 오늘 포함해서 한 3일 정도 더 하면은 4일? 4일 정도 더 하면 최소한의 기능은 완성이 될 것 같습니다. 이거 끝나고는 제가 하고 싶은 게 하나 있는데 그때 보여드릴게요. 그리고 음, 제가 앞으로도 할지 모르겠어요. 근데 적어도 오늘은 영어로 조금 이야기하는 비중을 높이겠습니다. 제가 곧 있으면 미국에 가서 살아남아야 하는데 지금 제 영어 실력으로는 살아남기가 힘들 것 같아요. 그래서 영어로 이야기하는 비중을 조금이라도 높여야 제 영어를 끌어올린 상태로 할 수 있을 것 같아서 그렇게 하겠습니다. Uh, so today we'll be looking at these three things. These three tasks are the main things that we'll be doing today. Continuing from last time, I briefly mentioned that I wanted to put conditionals in uh, my handwritten Lisp because as a programming language, it is not Turing complete. Now, um, I don't know much about Turing completeness, but I do know that if you don't have conditionals, it's not Turing complete. Um, the least I know is if you have conditionals and go-tos, then it becomes a Turing complete programming language. Um, go-tos are uh, the, the language's capability to jump between other sections of the code. So, uh, I mean, even if you don't have go-tos, if you have for loops, which are essentially go-tos, I mean, for loops can be implemented with go-tos as well. If you have conditionals and for loops, because that's what's more common these days, then it makes the programming language of Turing complete, is what I know. So uh, I think implementing conditionals is a bit more on the easier side. So I will start with conditionals. And then we'll add the capability of to run files. Right now, we are running code snippets in Haskell strings, and uh, that makes the language seem a bit limited. Like there's not much you can see because the code itself is inside the Haskell binary as well. So I think this feature will be a neat one. And I think we've come to a phase that we need this feature because once you have these two done, we have functions and we have conditionals. So I think there is a lot of features that the code can utilize for the code to become more larger. So I think this feature will be important for us as we further develop our Lisp. Okay, so I do want to keep this on the side, so I will keep the window as minimal as possible. Set num, no number. No relative number, no relative number. Okay, I think that's enough. Okay, so we are evaluating Boolean expressions now. To add that capability, I think first we have to tweak the parser. I mean, technically, you can treat the first thing we're going to do, let's kind of chop this task implement Boolean literals. Evaluation. So Boolean literals, what I mean by them is true, like things that like true and false. So the only literals that we have are numbers. And as you can see, they are kind of first-class citizens in our S expression. And technically, if you type in true and false in our current implementation as well, it gets parsed as an identifier, which is fine, but I think having a separate variant in the S expression data type makes it a bit more easier to handle it. So I will add a Boolean type. Boolean. Okay. Nice. So I haven't touched the parser in a long time, so it's gonna take some time to get used to again. First of all, let's make a Boolean parser. Xtheme. String is not an L. Oh wait. Okay, I think that parses a string. Couldn't match type text with bool. Okay, so this one yields a text. Now, this one is decimal. Okay, so let's first look at this package, because I think there might be a built-in function that provides the parsing of Boolean literals. Haskell Okay, so there are no Booleans. Okay. So we have to somehow convert these to Booleans. Haskell. Okay, I got an idea. If you have a string, then it's going to be true. Is this okay? Actual string. What is it supposed to mean? Okay. 그러면 oh wait. Okay, I think I know what's wrong. 됐다. True with actual type bool. What's this now? This one accepts two applicatives Okay, okay, okay. Okay, I got it. Um, pure. Import data functor. Okay. So there's dedicated operator to this, to the thing that I just did. Oh, oh, okay. It's like this one, but takes the functor and it takes a um takes some type and it wraps it inside the functor for you. So it's convenient. Um, should I put Lexeme in here? I think so. This is getting a bit out of control. Parse true. Parse false. I think this is a bit better. Okay, so we have the Boolean parser now, and where should we put it? I think we should put it before the identifier because it makes sense. Because remember that I said that a Boolean literal can technically be parsed as an identifier, but we are giving it special treatment. So we want it to be tried. We want the parser, the Boolean parser, to be tried before it attempts to parse it as an identifier. If this one is behind here, the Boolean string will get stuck here. So let's see if it works. Driving shell. I think I'll make a. Oh wait, there's a test parse function in megaparsec. I think test parser parse test. Okay, so what does this take? 이거 parser 가져오고 그다음에 바로 텍스트를 가져오네. 그러니까 true. Let's try this one first. 아, 오케이. 그러면 parse 하고 yeah. What if I create a new terminal here? Why is it hidden, this thing? Okay. We wanna go to Whisper. The formatter keeps messing with my code. What? Okay, so works as expected, but it's like the easiest thing we could have tried, so we'll try define x true, and then x. Oh, okay. Paren identifier define x boolean true. Why is it ignoring that? I think it's fine, so I'll just carry on. So we got the parser down. Wait. Oh. I didn't commit after after I worked on the code yesterday. Okay. Eval. Support user-defined functions is what it does, I think. It's been a day and I don't remember what I did yesterday. So now we evaluate a Boolean. We also have to make a value for the Boolean value. It's fairly straightforward. If it's a Boolean true, it's a, wait, yeah, it's a bool v true. It's just, if it's false, it's false. Fairly simple until now. Oh, okay. I don't think we need this one. We can just go with this. Are we good? I think we're done. Minerals down. Evaluation down. Expressions down. I think we have to add another thing, and that is what do you call them? Logical operators. For and that's it. And the nice thing about this, while implementing it in Lisp, is that there are no precedents, like operator precedents. So you don't have to mess with operator priorities, which makes it a little bit nicer to deal with. But the thing is, the developer has to consider all the priorities. Now let's look at this one. We define it as and, and we should make a get num, get bool. we get bool v, and then we 이제 웬만한 언어에는 이런 함수들이 있거든요. wait. any. 다 predicate를 받네. 이거를 그러면 Is there a better way? I think we'll just go with this one. So all corresponds to the end function. So we have to provide a predicate as the first argument. And the second argument we already have. So what do we put here? We can just put in an identity function. Haskell ID function. Is there an ID function? Okay, so perfect. So we can use all ID. Oh, that is a great idea. How does Haskell know this? Okay. And for OR, so note here that the operators above and below all have all taken a list of arguments. So like it doesn't have to be 2 operands. It takes a variety number of operands. It could even be 1. So if you put plus and 1, it'll be evaluated to 1. So it's basically a sum of all the arguments, and it applies to these operators as well. So here we use any. Oh, smart Haskell compiler, good compiler. And I think we have the operator down. We'll test this out right now. True. True. Wait. Does my parser not handle pipes? It doesn't. Okay, I'll add one. I was unsure about the number of characters that I supported, and which one I supported and which one I didn't. So I knew right away. True or false? false, true, false, 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 false. Okay, great. Now it's working. Heck. While we're at it, I think we'll implement comparison operators. Do you call them comparison operators? Close all these tabs. Comparison operators. Yeah. We will add equals. And then we'll add greater than. Oh, let's add not. Should it be an exclamation mark or should it be this one? I think I like this one better. And this one takes only one argument. So eval as expression argument. Then we have an access, we have value inside the state. So we fmap app value get bool, we get bool first, and then apply not, and then bool v. Yeah. And that's it. So we take the easy path here because we just ignore the other arguments that come after. Yeah, we could be strict about it and only accept one argument and throw in there if there are more than one argument. We're taking the easy road here. Okay, we got those down. Now we'll work on these. So this one takes 2 arguments. This one takes 2 arguments. And we have to compare them. Get num arg1. You have a number. arg1, arg2, and then we convert it into a Boolean. Okay, there's an error here. Get num. Oh, okay. So, oh wow. So this one, this one about no, okay. Get eval s expression. Okay, this is getting dirty. Okay, let's just do Why is it not happy? Okay. Map eval s expression, and then we fmap. We fmap map get bool, get num, and then before we convert it into a boolean, we apply all okay. 좀 쓸데없이 복잡해진 것 같은데. Argument 1, argument 2. Okay, let's just do a do expression. Let's try it. V1 is eval s expression arg1. Same applies to 2. What? And then we have a value, right? So we get bool. Okay, this one has a problem. But can we do this one? No. Wait, this is not even a boolean. It's supposed to be a number. We return a boolean value. Okay, looks good to me. For this one, you can almost do the same. Yep. Okay, now let's test it. The most fun part. Okay, that's great. That's great. I just realized that we don't have negative numbers. But that's fine. So we have these down. Everything's going smooth. Like much smoother than yesterday. I think yesterday's objectives were a little bit too hard. It took very long. So now we implement conditionals. Now this is one of the harder parts of today, at least. How are we going to implement conditionals? I think we'll add it as a native function. Or is it not that good? Yeah, let's do it. I mean, the code gets dirtier as we do it, as we add like more native functions. But it's kind of the easy way, and that's why I'm doing like, oh, whatever. So for if there should be three arguments. I mean, yeah, three arguments. There's the condition, and there's the if true, and there's if false. And just like we do in other operators, we just ignore the last part because we don't want to bother with it. So first of all, I think this one really needs nest expression because we have three expressions to begin with. We have a condition variable. It's getting colder. Throw an error to satisfy the compiler. We have a condition variable and right now I want to check if this one is a if this thing is a Boolean value, and I want to exit early if this is something like a number. And I'm thinking about how would I do that. We have a key either. Haskell do notation early exit. Either T. Yeah, I think none of these situations apply to the structure that we already have. And I don't feel like changing the whole structure over just to support those operators. I think I'll just go with plain if then block. If Haskell pattern matching and if why is it frowned upon? Stack Overflow is telling me that I should not use if statements. Okay, I'll just use case. CD of bool v b Does this work? Can I use the capture early? Okay, can't. Can I do this one? Okay. Oh, darn it. Well, Haskell case of default at top. Hmm. Who incomplete patterns? Okay, I'll just go with Lipton error, the classic Lipton error. Lipton error. Oh, Lipton left. Yeah. Condition expression must be a Boolean value. This makes me so anxious because it's nesting in like multiple levels. And the indentation is like 4 spaces. Makes me kind of uncomfortable. Okay, we're going with true and false, which I think is kind of the beauty of Haskell, like, and other languages that have pattern matching as well. Eval S expression if true. Okay, it's better than expected, isn't it? We'll test it. To be completely fair, it's not testing. It's just like trying out. Because I'm not testing it thoroughly enough. If true, 1, 2. If so, let's define a max function, a min function, because we don't have one. If a is smaller than v, um, return a. Otherwise, return b. Min. Working nice, it seems. Okay, conditionals down. Now we run files. We okay, so far so good. Now it's the hardest part. Run file. I think we'll accept the file name and then an IO. Haskell read file to string. Simple as that. Read file. File name. Do. It's a string. Now we eval s expression after parsing. Source. Let's just go with input. And then French ever. I'm copying the code right over here. So I might as well just do this. Okay, so this is a string. This thing compiles, but it'll not actually be the behavior that we wish to have, because most likely the input will be it won't be a singleness expression, but rather a list of s expressions. So okay, expressions. How do we parse? As expressions. Well, We pass multiple S expressions. Easy as that. Pause program. S expression. Pause program. Program input. Run parser. It's the same with this, but we use a different parser. So we have plus program. And we no longer want these to be paused. I mean, yeah, exported. We use pause program. Then we could do this. Just do this one. Oh, wait. So we pass the S expression, and we evaluate. So we have a list of these expressions. We evaluate this one, and then we have to pass the environment that that is the result of evaluating E1, and then pass that environment to E2. So we have to make sure that the correct environment gets passed each time. The first thing that comes to mind is fault, but I feel like that's really naive implementation. What if I do this thing? Oh, wait. Let's see if they recognize as pause program. Okay, looks good. We have as expressions. So I think we can eval as expressions map m. Our friend map m comes to the rescue again. So if you do map m, so eval as expression results in a state t, and then we have an array of s expressions. So it will become a state t of the array of s expressions. Oh wait, array of values. Yeah. So we have the array of values. So our job is to print them all in order. Okay. So now we have the list of values, and we want to print them in order. The first thing that comes to my mind is sequence. Oh wait, it's not this one. Okay, we map print and then we map sequence. Oh, nice. Can use this one. Oh, wait. Oh, okay. So we have the state t. So now we have to run state t. I mean, eval state t. Because we don't really want the environment. Flip. We have to flip. So this result is a list of values, right? So now we have to map m print the result. Or not. So it's now time to combine all of these. Flip. Map m eval as expression. And then pause program. Okay, that's happy. Let's try this one out. Test racket. Okay. What's the file extension that has the file type Lisp? Lisp. No. Oh, is it Lisp? Okay. How about this one? Oh, okay. Is it working? Okay, I don't know. Let's define what should we do? Define is even. We can't do is even. We don't have a logical, I mean, remainder operator. Yeah, we'll just do min. And we'll do multi-line. And then we'll call min 1, 2, 2, 3. Drop a few new lines here and there. And we'll see if this one works. Great. So maybe we won't print if the return type is unit. I mean the value. Okay, great. Now, I'm going to accept command line arguments. I'm not going to use them in development because I have a lot of debugging to do, and I obviously have to run the file quite frequently. So I won't use them while in development, but it's a nice feature to have. Except command line arguments. So I'm going to keep it simple, and I will run a file if a file name is provided as a first argument to the program. And if there are no arguments, then I will just open up a REPL, just like how Python does it. Get args. If length args, let's print the arguments just to see how it works. So the length will be 0 if there are no arguments provided, because most programming languages, if they recommend arguments, the first argument is the file name. I don't think it's the case for I don't think it's the case for this one. So if the length of the arguments is 0 or is empty, does it work? Okay. I'll just do if it's purple. Okay. So apparently there's a function called null. Okay, this one bugs me a little. But maybe we want to check if the file exists first. This file exists. Okay. Unless, Haskell, unless. I think the one to use is when, because when Rx is null, we want to launch the REPL. But does it report? I don't think it does. I need to add directory. Why is it not working here? It looks like it should work. Oh no, it's not working. Okay, it's not working. Oh, okay. Control monad. Okay. Now what if it doesn't have an argument? It does both. So it is not exiting early. So I think we'll have to go back to using if statements. If it exists, then otherwise, print. How do I print a standard error? I won't. Does file exist? What's error? Oh, do. So it opened up a REPL because we didn't provide an argument. Now we provide a file name, and it'll run the file, the code inside the file. And if we pass in a non-existent file, a file that does not exist, then it'll. Well, why is it cluster line? Oh, no. Okay. So I was wondering why there were quotation marks around the string the other day. And it was because of the print function, because it applies show to the argument that is provided. And applying show to a string apparently wraps it in quotation marks. So I will replace these with cluster line. Cluster line. Now, what if there's an error inside, like this one? Functionality doesn't match. Arity is 2. And we can see that if there's an error in the middle of the file, it doesn't proceed to do other things. And I think that's reasonable. And when we are running inside a REPL, we don't want it to terminate. So the REPL doesn't do that. When we run a file, it does do that. So it's important to note the different behavior when it comes to handling errors. Okay, I think we have our objectives done in a fairly smooth and fast way. Before we finish off, I think I want to check one more thing, and it's if it supports recursion. So I never mentioned a single word about recursion up until this point, but if our language support recursion, in theory, you don't need gotos or for loops because recursion can do what gotos and for loops do. But I think the recursion might work even if we didn't think about it from the first place. I'll just see if that feeling is right, and if it's right, we have completed. We have made a Turing complete language. If not, we'll try to figure it out in the next recording session. So, what should we try? I think we'll try some. Oh, we can't do some because there's no lists. We can do some. Range sum from start to finish. Start to end. We'll add in an accumulator. So it's easier for us to write the recursion. So if start, why is it giving me errors? If end is less than the start, we return the accumulator. Otherwise, we call range sum, adding one to start, and then adding start to our accumulator. Okay, here we go. Range sum 0 to 10 and 0. Should output 55. And it doesn't. Why is it? It has a pause error. Is it this one? Wonder why. Oh, wait. Oh, okay. The parentheses were not balanced. Okay, I think this is taking so long. There are multiple possibilities, but the reason that I'm hoping for is because it is recursing too deep. If we reduce the recursion stack depth, it'll probably take less, but I'm doubting it right now. 왜 안 되지? 이게 0, 이게 2, 이게 1. 왜 안 되지? 왜 안 되지? Where is it stuck at? Okay, I guess we will find that out. Try to figure that out in the next recording session. Today, we've gone through a lot. And I've talked in English, for the most part. So I guess, 네. 여기까지 하도록 하겠습니다.